Today we will talk exclusively about work and energy. First, let's do a one-dimensional case. The work that a force is doing when that force is moving from point A to point B, one-dimensional. Here's point A, and here is point B, and the force is along that direction, or either in this direction or in this direction, but it's completely one-dimensional. That work is the integral in going from A to B of that force, dx, if I call that the x-axis. The unit of work, you can see, is Newton meters. So work is Newton meters, for which we call that a joule. If there's more than one force in this direction, you have to add these forces in this direction vectorially, and then this is the work that the forces do together. Work is a scalar, so this can be larger than 0, it can be 0, or it can be smaller than 0. If the force and the direction in which it moves in an opposite direction, then it is smaller than 0. If they're in the same direction, either this way or that way, then the work is larger than 0. F equals ma. So therefore, I can also write for this m dv dt, and I can write down for dx, I can write down v dt. I substitute that in there, so the work in going from A to B is the integral from A to B times the force, which is m dv dt, dx, which is v dt. And look what I can do. I can eliminate time, and I can now go to a integral over velocity, the velocity a to the velocity b, and I get m times v times dv. That's a very easy integral. That is 1/2 m v squared, which I have to evaluate between VA and VB, and that is 1/2 m VB squared minus 1/2 m VA squared. 1/2 m V squared is what we call in physics kinetic energy. Sometimes we write just a K for that. It's the energy of motion. And so the work that is done when a force moves from A to B is the kinetic energy in point B, you see that here, minus the kinetic energy in point A, and this is called the work energy theorem. If the work is positive, then the kinetic energy increases when you go from A to B. If the work is smaller than 0, then the kinetic energy decreases. If the work is 0, then there is no change in kinetic energy. Let's do a simple example. Applying this work energy theorem, I have an object that I want to move from A to B. I let gravity do that. I give it a velocity. Here is the velocity v of A. And let the separation be h, and this could be my increasing y direction. The object has a mass m, and so there is a force, gravitational force, which is mg, and if I want to give it a vector notation, it's mg y roof. This is my increasing value of y. When it reaches point B, it comes to a halt. And I'm going to ask you now, what is the value of h? We've done that in the past in a different way. Now we will do it purely based on the energy considerations. So, I can write down that the work that gravity is doing in going from A to B, that work is clearly negative. The force is in this direction and the motion is in this direction. So the work that gravity is doing in going from A to B equals minus mgh. That must be the kinetic energy at that point B, so that this kinetic energy at point B minus the kinetic energy at point A. This is 0 because it comes to a halt here. And so you find that 1/2 m VA squared equals mgh. M cancels, and so you'll find that the height that you reach equals VA squared divided by 2g. And this is something we have seen before. It was easy for us to derive it in the past, but now we've done it purely based on energy considerations. I'd like to do a second example. I lift an object from A to B. I, Walter Lewin. I take it at A. It has no speed here. VA is 0. It has no speed there. And I bring it from here to here. There's a gravitational force mg in this direction. So the force by Walter Lewin must be in this direction. So the motion and my force are in the same direction. So the work that I'm doing is clearly plus mgh. So the work that Walter Lewin is doing is plus mgh when the object goes from A to B. The work that gravity was doing was minus mgh. We just saw that. So the net work that is done is 0. And you see there is indeed no change in kinetic energy. There was no kinetic energy here to start with, and there's no kinetic energy there. If I take my briefcase and I bring it up here, I've done positive work. If I bring it down, I've done negative work. If I bring it up, I do again positive work. When I do positive work, gravity does negative work. When I do negative work, like I do now, gravity does positive work. And I can do that a whole day, and the net amount of work that I have done is 0. Positive work, negative work, positive work, negative work. I will get very tired. Don't confuse getting tired with doing work. I would have done no work, and I would be very tired. I think we would all agree that if I stand here 24 hours like this, that I would get very tired. I haven't done any work. I might as well put it here and let the table just hold that briefcase for me. So it's clear that you can get very tired without having done any work. So this is the way we define work in physics. All right. I'd like to return to gravity and work on a three-dimensional situation. We have here, let this be x, this be y, and this be z. And there is here, this is the increasing value of y. And there's here point A in 3 dimensions, like this. And there is here point B. So you get a rough idea about the 3 dimensions. And y of B minus y of A equals h. That's a given. So there's a height difference between A and between B. There's a gravitational force. The object moves from A to B. Suppose it moves in some crazy way. Of course, gravity alone could not do that. There has to be another force if it goes in a strange way. But I'm only calculating now the work that's going to be done by gravity. The other forces I ignore for now. I only want to know the work that gravity is doing. The object has a mass m, and so there is a force mg, and I can write down the force in vector notation. It's in this direction. So now I notice that there is only a value for f of y, but there is no value for f of x, and there is no value for fx. They are 0. And so f of y equals minus mg. And so if I calculate now the work in going from A to B, which is the integral in going from A to B of f dot dr, then the only term that I have is the one that deals with the y direction. The other terms have nothing in it. So it is the integral in going from A to B of fy dy. And that equals minus mg, because we have the minus mg, times y of b minus y of h, so that is minus mg times h. And what you see here, that it is completely independent of the path that I have chosen. It doesn't matter how I move. The only thing that matters is the difference in height between point A and point B. H could be larger than 0 if B is above A. It could be smaller than 0 if B is below A. It could be equal to 0 if B has the same height as A. Whenever the work that is done by a force is independent of its path, is only determined by the starting point and the end point, that force is called a conservative force. It's a very important concept in physics. I will repeat it. Whenever the work that is done by a force in going from one point to another is independent of the path, it's only determined by the starting point and the end point, we call that a conservative force. Gravity is a conservative force. It's very clear. Suppose that I do the work, that I go from A to B in some very strange way, then it is very clear that the work that I would have done would be plus mgh, because my force, of course, is exactly in the opposite direction as gravity. So whenever gravity is doing positive work, I would be doing negative work. If I hold it in my hand, when I'm doing positive work, gravity is doing negative work. Again, I'm going to concentrate now on a case where we deal with gravity only. When there's only gravity, then we have that minus mgh is the work done in going from A to B, equals minus mg times y of b minus y of a. And that now is the kinetic energy at point B minus the kinetic energy at point A. This is the work energy theorem. Look closely here. I can rearrange this and I can bring the b's on one side. I can bring the a's on one side. I then get mg times y of b plus the kinetic energy at point B equals mg times y of a plus the kinetic energy at point A. And this is truly an amazing result. We call mgy, we give that a name, and we call that gravitational potential energy. Often we write for that PE or we write for that a U.